In this video, we will be taking notes on rational exponents. Before we can look at rational exponents, let's do a quick review of the rules of exponents in general. In the first example, we have a to the x times a to the y is equal to a to the x plus y. To write this in words, when multiplying two things with the same base, you add their exponents. In the second example, we have a to the x over a to the y is equal to a to the x minus y. Or, when dividing two things with the same base, you subtract their exponents. In the third example in the chart, we have a to the xy is equal to a to the x all to the y. When raising a power to a power, you multiply the exponents. It's important to remember that this only works for monomials, so for nothing with addition and subtraction. If we have addition inside, we cannot just distribute a squared sign to both of those x and y, but if what we had inside was a monomial, there was no addition, it was x to the negative 2, y to the third, all to the third power, then we could take that and we could distribute the 3 in the exponent, take a power to a power, and we would have x to the negative 6th, y to the 9th. That's not all the way simplified because it still has a negative in the exponent, which brings us to the next rule. In the next rule, we have a to the negative x is equal to 1 over a to the x. Something raised to a negative power is the same as its reciprocal raised to a positive power. Next, we're going to do a quick refresher of how to evaluate some of these expressions on your calculator. So if I wanted to do 16 to the 1/2 power on my calculator, I'm going to need to type it in as 16 caret 1/2 in the fraction. I could also enter that as 16 over 1 with a caret 1 divided by 2. Either way, I'm going to get the same thing. So let me pull up my calculator. 16 to the 1/2. I'm using the fraction button on my calculator, and that gives me 4. Either one should give me the same answer. They're both two just different ways of writing that expression. For number 2, we've got 32 to the 3/5 power. So on my calculator, I have 32 caret 3/5 with the fraction, and the answer to that question is 8. We have to be careful with fractions and fractions and fractions and exponents. Number 3 is 16 divided by 4 to the 3/2 power. We need to be sure that we've got that 3/2 in parentheses again. So on my calculator, 16 divided by 4 to the 3/2 power. I don't have to worry about it doing the exponent before the division because the calculator understands order of operations and it knows that this is equal to 2. The last one, 81 to the negative 1/4 power, I'm going to put in my calculator as 81. I'm going to use the negative 1/4 in my fraction for my exponent. And that gives me 0.3 repeating. If I want a fraction for this answer, I can hit the FD button on my calculator. On my calculator, that was right here, FD, and that will turn it into a fraction, which is 1/3. If you're using your TI, by the way, you could do math, enter, enter, and turn that 0.3 repeating into a fraction as well. All right, on to the next part, we're looking at the definition of a rational exponent. We can see that these exponents up here were giving us nice answers, so something's going on with those fractions. And here's our rule. For any non-zero real number b and any integers m and n with n greater than 1, if we take b and we raise it to the m over n power, that's the same thing as b to the m power, but it's the nth root of that. We could also do the nth root of b first and then raise it to the m power because those are both part of the exponent. But the way we write this, the power is on the top of the fraction and the root is on the bottom of the fraction. Now that we understand this definition of a rational exponent, let's go back and look at the 1 through 4 that we did on our calculator and see why these should make sense if we were to do them instead of with our calculator, with our brain. For number 1, 16 to the 1/2 meant the index was 2 and the root was 1. So square root of 16 is 4. That's what I got on my calculator. Looks good. How about 32 to the 3/5? That's 32. The exponent or power would be 3 and the root would be 5. It doesn't matter what order I do these first, the 5th root or the cubing. I don't know 32 cubed in my head, but I know that 32 is 2 to the 5th power, so I can take a 2 out from underneath my 5th root. It will still be 2 cubed, which is 8, and again, that matches up nicely. For number 3, I had 16 on the top of the fraction, and on the bottom I had 4 to the 3/2. So that's 4, 4's power was 3, and the root would be a square root. Again, I don't want to cube first, I would rather square root 4 first. The square root of 4 is 2, and I still have an exponent of 3. So this is 16 divided by 2 cubed, which is 16 over 8. Or 2, and again, that's the answer we got on our calculator. For number 4, I had 81 to the negative 1/4. 81 to the negative 1/4. First of all, the negative in the exponent means this is the same as 1 over 81 to the 1/4 power. Then I also want to think of the 1/4 power as meaning the 4th root of 81 to the 1st power. 81 is 3 times 3 times 3 times 3, so I can take that out from underneath, and I have a 1/3. So, in examples below, we're trying to write these expressions in simplest radical form. For number 5, the first thing that we're going to want to do there is try and put those two x's together. We have x to the 2/3 times x to the 5/3. We should realize when we multiply two things, we add their exponents. So this is the same as x to the 7/3. That's a rational exponent right now. If we want to write that as a fraction, not as a fraction, but as a radical, the root is going to be a 3 because that's the bottom of the fraction, and the x is going to be to the 7th power because the power is the top of the fraction. Because I have to write this in simplest radical form, I want to see what I can take out from underneath. If I have 7 x's and a cubed root, I can take out 2 sets of 3, and I'll still have 1 x left underneath. And this is the expression in simplest radical form. For one like number 6, we have two different letters, so we can't put them necessarily together with one single fraction, but they both have 2's on the bottom of their fraction, so both of these belong underneath a square root. We don't have to write the little index in there as 2 because it's a square root, but we could. The power of x was 1, the power of y was 3. My last step is to clean this up a bit. I only have 1 x, so it has to stay inside the square root. I have 3 y's, so I have enough to take 1 y outside, but I still have 1 y left inside. On a problem like number 7, we have c to the 1/4 and e to the 2/3. In order to put these things underneath the same radical, our radical is going to have the same index, the same little number in here inside the radical. So I'm going to have to get c and e to both have the same denominator of their fractions. The least common denominator of 4 and 3 is 12. If I want to change my 1/4 into 12ths, 1/4 I'd multiply by 3/3 to get 3/12. If I want to change e's exponent, my 2/3, into 12ths, I'll multiply by 4/4 and I'll have e to the 8/12. Now that both of my variables have a 12 in their denominator, I can make the index of my radical a 12. I then have c to the third, e to the eighth. In this case, I can't take either thing out, so my final answer is the 12th root of c to the third, e to the eighth if I want them under a single radical. Pause the video while you try to do number 8 and number 9. In number 8, you're going to have to get a least common denominator to put them all under a radical and simplify when you're done. In number 9, you're going to have to use your rules of a power to a power first to simplify the exponent and then write it as a radical and simplify your answer. For number 8, we got a common denominator of 6 with all the fractions, so I put them all underneath the 6th root. Then I realized I had more than 6 of each of my letters, so for the x's I could take out a set of 6 and 3 would be left inside. For the y's I could take out 2 sets of 6, so 12 y's are coming out and 2 are left inside. For the z's I take out 1 set of 6 and that leaves me with 3 z's left inside. Don't forget to rewrite this little radical with the index in here. We have a tendency to forget to write that and then our answer is not correct. On number 9, I had m to the negative 2/5 times negative 1/2. So when I take a power to a power, I multiplied those exponents, and that gave me positive 1/5 in my exponent. So the power of m is 1, and the root is 5, and I could rewrite that without the 1 in the exponent as the 5th root of m. On the back of this, we're to write the expression with simplified rational exponents. So on this side of the paper, we're starting with the radical form, and we need to write it with rational exponents. We need to remember that if in number 10 I have a square root, that means my index is a 2. So when I rewrite this, I will have y to the 7/2 power. I can't simplify 7/2, so that's all done. In number 11, I again don't have an index, which means my index is 2. So I have x to the 9/2, y to the 12/2. I want to check and see, can I simplify any of those fractions? X to the 9/2 cannot be simplified, so I'll leave it as 9/2, but y to the 12/2 is the same as y to the 6th. On number 12, I have a cubed root, so each of my fractions in my exponents will have a denominator of 3. I also need to be careful because 3 has a power of 1 even though it's not written, so my 3 will be to the 1/3 power. My x will be to the 2/3 power, and my y will be to the 4/3 power. None of those fractions can be simplified, so again, I'm done with that one. Pause the video while you try and write 13, 14, and 15 with fractional exponents. Remember to simplify any fractions when you're done. On number 13, realize that the 7 is to the 1st power, so when I write this in fractional exponent form, I'm going to have a 7 to the 1/3. All of my roots are 3rd roots, so all of my denominators of my fractions are 3's. In the final step, I can simplify 6/3 to 2 and 9/3 to 3. In number 14, my index is a 5, so all of my denominators have 5. In the final step, I can simplify the 10/5 to a 2, whereas x and y's exponents have to stay the same. In number 15, my index is a 4, so all of my roots are 4ths, and my exponents are 1/4 in the bottom of the fraction there. I can simplify 8/4 to 2, I can simplify 6/4 to 3/2, and I can simplify 10/4 to 5/2. So I need to do all of those simplifications. When we're working with rational exponents, we can either write answers in radical form or rational exponent form. We just need to read the directions to see what each question is asking.